Okay, well, I think we're going to get going. I think we have most of everybody here, and if people trickle in, we'll be doing some introductory stuff, so I think they should be able to catch up. But welcome, everybody. Thank you for joining. First, I just want to introduce kind of the session and then kind of how it's going to work and then what we're doing here. So in case, to make sure that you're in the right place, this is the Saturn Cloud's Scaling Machine Learning Workshop. So it's going to be a hands-on workshop where I'll talk through some slides at the beginning. We're gonna take like a hands-on approach in the Saturn Cloud hosted platform. So you all have accounts there, and then we'll kind of get you going there. And then we're gonna do some exercises of taking like Scikit-learn workloads, Pandas and Scikit-learn, like single node workloads, and then moving them over to clusters using Dask. So first, I just want to give a quick introduction of myself. My name is Aaron. I'm a senior data scientist here at Saturn Cloud. I'll be the instructor for the course, so I'll be the one sharing my screen, talking through a lot of things. And then I want to pass it over to Stephanie to introduce herself too.
Hi, I'm Stephanie. I am also a senior data scientist at Saturn Cloud, and I am second in command today. I am going to be supporting anyone who has questions in the middle of the workshop while Aaron is presenting content. So you can connect with me either on the Slack channel or in the chat here in the window. But we're going to try and keep things in the Slack channel so that everyone can participate and learn from each other.
Great. Okay, so the way that we're going to start is first of all to make sure that everybody is good to go. Is everybody in, or if you're not in the Slack, please let us know right now. Also, if you didn't receive an email invite to Saturn Cloud, you should have gotten an email that looks something like, reset your password for user with the username, and there was a link there for you to log in. Did anybody not receive that? Okay, cool. Well, if we go along and then you don't have it, just please let us know. We can help you with the Slack. We have some Stephanie's here to help and support, and so post a message in there. And there, if you have any kind of technical problems or anything like that, the best place to do it is if you want to kind of unmute real quick and say something here, and then we can do like our kind of like just checking out and debugging through the Slack channel through some threads there. Just we want to make sure that everybody's able to actually like follow along and actually run some of the stuff that we're showing. Cool. Okay. So the first thing that we're going to start with is just to go through a few slides, maybe just like 5 or 10 minutes. And then we're all going to kind of go into Saturn Cloud together, but I at least want to introduce like Saturn, what we're doing, what's Dask, all that good stuff. So I'm going to share my screen now. I'm actually going to share my whole screen, so it's risky, but okay, great. Okay, there's just going to be just a handful of slides. Actually, I'm going to post the link to the slides as well if you want to follow along in the Slack. There's not too much here, but at least it gives you just some follow along and look at this yourself. So here we are, scaling machine learning in Python. The idea and one of the prerequisites for the course, and we kind of put a little poll in the Slack channel as well. It seems like everybody's in line here, is that we're kind of starting this workshop from the place of you're already kind of doing machine learning in Python. And the typical stack for this is in the PyData stack, like things like Pandas, NumPy, Scikit-learn, and we're going to be doing everything here inside of JupyterLab. And so this is just kind of like the typical like machine learning stack, and we're really focusing on these tools in this workshop. But the challenges that come up with using these tools is that they're very mature and they've been around for a while, but they're also built in in manners for like single node, single core kind of in-memory computations. So there's a lot of limitations that come in. Is like if your data is too big to fit inside a Pandas data frame, you either have to like run things in chunks, or you have to do some like weird workarounds. And the same thing where like maybe you're just kind of out of memory when you try to train a model, or training a model takes a long time, or you have a grid search that ends up taking forever. And so the idea here is how we can take these tools that we're already kind of using and are mature, and then scale that out and then run things faster, run things with larger data sets. That's the whole idea. So when we're talking about scaling machine learning, it's not only just can we train fit out a model to a large data set. That's one component of it. But there's actually a lot of different places where scaling might be necessary in machine learning. So the way that we think about it is on these compute bound or memory bound situations, or both. But somewhere on the compute bound situation is you just need more CPU cores to do work. So if you're training like a random forest, or if you're doing a grid search, like training many models, training complex models, your data might be fairly small, but you're going to need a lot of computations to happen. And so that's where scaling is helpful, because you add more cores to just, spread out the work more, and then it finishes faster. On the memory bound side is when you have like really large data sets. So the first thing is like maybe you just start off with a large data set from a database or from CSV files or something like that, and you have to do a bunch of pandas processing to kind of engineer your features, filter it down, or whatever. And then once you get to the end of it, your data is pretty small, and it trains comfortably in Scikit-learn, but you still need to do that kind of like large data set processing. And then if it may be that you had to do that kind of in some outside of Python. And the idea is to try to keep this all here together. And then the other scenario is when you're training with really big data sets. A lot of the times that you might not need to do that, but in the case that it's necessary, you can actually fit models to data sets that wouldn't even fit in RAM or might just take forever. And so, so what we're using for the scaling here is Dask. And if you're not familiar with it, I know a couple people said that they have some prior experience with Dask, but we're kind of expecting that most people in this session don't. And so Dask is a parallel computing library. That's like the core of it. But it was built to kind of parallelize and scale Python packages, especially in this kind of data science and machine learning ecosystem. So it starts off, the core of it is a really low level interface for defining tasks that would execute, and then building up like a task graph. And then so the idea is that when you run some functions and build up some tasks, Dask will keep track of the dependencies between them. And then when you say you actually want an answer is when it'll go run it. And so it'll know, okay, 2 of these tasks I can run in parallel. This other one depends on the other tasks, and then it'll wait for those. And so there's a lot of higher level interfaces built on top of this low level library. And we're going to focus a lot on those, specifically the data frame library and the machine learning library. And so these integrate really well with tools like Pandas and Scikit-learn. And they have very similar APIs, or almost matching APIs, as Pandas and Scikit-learn. But the idea is that Dask is taking that code and parallelizing it. And most of the stuff you're going to see kind of hands-on running through it. So I won't spend too much time here. But the idea is that Dask interacts with these packages. It'll scale these things pretty easily with minimal code changes. Depending on what you need to do, you might need some more code changes and some more concepts. So this here is a really busy slide, only because, like I talked about, there's a lot of different scenarios when you're thinking about machine learning. And our key thing here is just like you should scale when you need to scale. So if you have like a pretty small data set and your processing works just fine in Pandas, like it's like a 1 gig CSV, and you can create all your features, do whatever you need to do, your group bytes, whatever, and it works pretty well on a single core in Pandas, that's great. But if you end up then having to train a really complex model or do a really large grid search, that's where you might want to introduce Dask. And we're going to go through a lot of those scenarios of where we have our Scikit-learn code, we have our Scikit-learn pipeline and stuff already, and then we can kind of bolt on Dask to do to parallelize when it's necessary. But then if you get into kind of larger scenarios where you have flat out start with a giant data set and you kind of need to process that with a cluster, then you can start off with Dask. And then if that data gets really, really small, at the end when you're done processing, you can train with Scikit-learn, and then you're done. There's a couple other scenarios that we're going to go through, specifically like grid search and ensembles. Those again are the more compute heavy things where maybe your data set and your individual model training fits really comfortably on a single node, but then you need to train 300 models and you don't want to wait hours for that. You can scale that out to a cluster with Dask. And then another key thing, and a lot of we see a lot of people doing using Dask for, is kind of like inference and scoring. So either maybe it's some kind of data enrichment pipeline, or you have some need to do batch or scheduled inferences. Again, if the data is pretty small and there's not a lot going on, you can just use Scikit-learn. But with Dask, you can actually use some trained Scikit-learn model. And let's say your training data set is pretty small, but you now need to do inference on a really large data set. You can then train the same way you would normally do with Scikit-learn, and then scale that out with all of your instances that you need to run scoring on with Dask. So again, we're going to go through all of these scenarios, just trying to give some guidance and think through your kind of workloads. The whole goal of this workshop is so that way you feel empowered to take your workloads that you already have that are either slow, not running, you're sampling data, And then you can now kind of take what you learned from here, using Dask, using Saturn Cloud, now kind of scale out those workloads. So definitely like stay active on the Slack. We'd love to kind of keep talking about some workloads that you're doing even after this session. So this is a quick about just like, why are we even doing this on Saturn Cloud? And, so because like Dask can run on a laptop, Dask can run on different computers if you stitch them up together. But the key here is that there's a lot of deployment options, and it's still really challenging to handle cluster deployment. You're dealing with multiple machines, you're dealing with the cloud, you're dealing with kind of all these types of different scheduling or infrastructure tools. And the idea here is that, as a data scientist, someone who's building models, you don't want to have to worry about all these deployment schemes. And so that's kind of where Saturn Cloud comes in, is we try to take away, abstract away a lot of this DevOps work, a lot of this infrastructure work, and just write your code, use your Dask clusters, scale up your work. So today we're going to be using the Saturn Cloud hosted platform where you all have accounts. We've loaded up $50 of free credits for you, which are not going to be used throughout this whole tutorial. So definitely use those credits afterwards and kind of keep working and then using it. We're hoping that you're going to find a lot of value with the platform. And then if there's a need for like an enterprise, your own kind of installation for it, you can talk to our sales team about that. We do enterprise installations as well. Okay, so like I said, the slides are quick. That's all I had for that. The key thing now is to make sure that everybody is going to be ready to go inside of Saturn. So I'm gonna drop the link to Saturn to the kind of hosted platform, and I want to make sure that everybody can get in there and everybody kind of knows their username and everything. So you should have, again, like I said, you should have received an email that said, your password reset thing. And so can everyone just kind of jump into Saturn Cloud and just give me like a verbal confirmation or a confirmation in the chat that you can access Saturn Cloud and that you've gotten into your account. Okay, so all these, in case you are having some trouble, all this stuff is on GitHub, and there's instructions for how to run it too, in case you want to follow afterwards or kind of check out all stuff again. But for now, we're going to go ahead and keep moving. So I want to make, you can look at my screen. So, there's going to be like a lot of different pieces moving around in this because, we're doing this kind of virtual hands-on workshop thing. So you're going to want to have my Zoom window kind of around, and maybe you can rearrange your windows so you can see things if you have multiple monitors. But then you're also going to want to just keep a browser tab open to the Saturn Cloud here, and then kind of keep working from there. So I want to just go through what we're seeing here in Saturn and then explain everything to you. The notebooks in the repo do explain things as well, and we'll kind of skip over that. So this is the landing page for Saturn. Everything here in Saturn Cloud starts from a project. And so a project is composed of several different resources. And you can think about the resources as the hardware where you're doing things. So the two main components that we have with a project are a Jupyter server and a Dask cluster. So a Jupyter server is where you actually go in and write your code. It is a machine. In this case, this is a machine here that has 4 cores, 30 gigs of RAM, and it's hosting this Jupyter Lab interface. So you can click that, and now you get to the Jupyter Lab that you're kind of used to launching from your laptop. It's really important to see this image here, and every project is backed by an image. And so behind the scenes, what that is a Docker image that has all of these Python packages installed. So you can configure your own images from this images tab, but we also have a lot of pre-built ones here for you. So like if you wanted to make a custom image, you can go in here, give some pip requirements and say like Dask and Scikit-learn or something like that. And then behind the scenes, we kind of take care of packaging up a Docker image. And the key there is that when you're using a cluster, this Dask cluster has to have all the same packages and all the same versions as what you're running on your Jupyter server. So if you start off with an image, then you're kind of sure that everything else is going to have the same things. But we don't have to worry about images too much. We already have a pre-built one here for you, and then it should be good to go. So the Dask cluster is an optional component. You don't always have to run a Dask cluster. If I stop this Dask cluster, my Jupyter server would keep running. But this is how you would scale out your work. So you can specify, and I'll go ahead and kind of edit a different project so you can see how this works. Like if my cluster would stop, leave yours running because you want to make sure that you can use it. But if I were to go to edit this project or this cluster, I can now see all the different options that I have. So I can choose a scheduler size, I can choose worker size, and again, we're going to go into a little bit more on that stuff. And then these are some settings. So the way that we have it set up right now is that we have 3 workers on our Dask cluster. So that's 3 other machines besides your Jupyter server. That's kind of how we're going to be scaling out our work. Pandas and Scikit-learn are only going to be running on the Jupyter server. But then when we actually scale out and utilize Dask, you'll see the code for that is when it's going to go through to this cluster. And so those are the 2 main components that you really need to think about for today's workshop is, well, first of all, your project, and everybody should have this workshop scaling ML project, and then this Jupyter server and this Dask cluster. There's a couple other components inside of Saturn Cloud, like deployments and repositories and other things that we can kind of discuss later, but these are our 2 main points. So what I want everybody to do now is, first of all, make sure that you can actually see this workshop scaling ML project, and that you can click on this Jupyter Lab button. And when that opens up, we have preloaded all of the notebooks onto all of your accounts already. So you should see this folder here that says like workshop scaling ML. And then when you click on that, there should be a handful of notebooks here. So what I want everybody to do is open up this O1 start notebook. And then I'm going to pause for a second, make sure everybody can get here. Again, let us know if you have any problems, post in the Slack if you have any problems too. Okay, great. Okay, so like I said, these notebooks are kind of written to stand alone. And like, you know, if you're running this outside of this workshop, you can kind of read through things and then go through it. A lot of the stuff that's written out here, I've already just kind of walked through within Saturn, so we can skip a lot of that. The key thing I want to make sure is that everybody can scroll all the way down to this hello world section and make sure that you can run this cell and that it actually prints hello world. And so you should see that. You should see this Dask cluster is ready, hello world. So that's to make sure that your cluster is running. It's hooked up to your Jupyter server to make sure that you're good to go. So if you don't see this, please, you know, say something now and then post something in the Slack channel as well. Okay, so I'm going to take the silence as a confirmation that everybody's good. Again, if you have any problems, please just kind of say so. This is a totally interactive, hands-on type thing. Okay, so we're going to be using some publicly available New York City taxi data to do some of our work. You can run this out and kind of just see this S3FS package allows you to just like work with files on S3. But these are some CSV files that are just kind of, it's a pretty large data set, so we can grab some. I think each of these is like 500 megabytes each file, so that way we can layer on a few of them and deal with like these larger data scenarios. So a lot of this workshop is written in this kind of exercise format where a lot of the code, it's kind of already pre-written out for you. I'd say 80% of the cells throughout these notebooks are already written out for you, but the idea is to kind of read through it, run through some cells, you see the output, and then you can kind of play with things yourself and kind of tinker with it. There are a couple points, mostly just to make sure that you're still focused and keeping up, is these exercise sections where we'll have some code that's pre-written out, and then there's this area where you need to kind of fill in some code, and then you can run that. So you can kind of work with that, and you know, it's the whole idea is you want to play around with it, figure things out, see how things are working. So you can absolutely do whatever you need to. So then if you fill out the code and then run it, you can see what your results are. And then below here, there's these 3 dots that there's going to be a hidden cell that tells you what the actual real like solution is. So if you expand that, you can run it, and then you can compare that to what you wrote. So I'll say if you did wrote something and maybe it wasn't quite right what the solution was, or you just kind of cheated and you wanted to look at the solution, make sure you do run the solution cell, because later cells in the same notebook might depend on it. So just kind of make sure that you do that. But now we're kind of ready to get going. Okay, so we're going to start from this second notebook, the single node. And so this other notebook, the idea here is that it shouldn't be really new to you as far as the code that's in it. It's using a lot of Pandas, Scikit-learn type code. But the idea here is we're going to walk through this. We're going to hit a couple roadblocks. We're going to hit a couple walls. Things are going to be slow, or things just aren't going to work. And then we can see how, you know, and then we'll use this as like a starting point for when we parallelize our code with Dask. So the first thing that you would want to do though is open up you want to like monitor the resources of this Jupyter server. So like I said, we're dealing with like two kind of resource components. There's the Jupyter server where these notebooks are running on, but then it's also a Dask cluster for when we're going to scale out our work. So this notebook strictly runs on the Jupyter server. So we want to just like monitor the resources of this. So like the idea is that we're going to end up running out of memory. We're going to end up using a lot of the CPU cores and kind of things are taking a long time. So it's really helpful to actually watch that. So what you want to do is open a new terminal window and then run this program called htop. And so what that does is it shows you the resources. So you can either go over to the launcher here with this, or you can go File, New Terminal, and then you can type htop, just like this. And then this gives you the kind of resource utilization of your Jupyter server. So what I always like to do, and I'm going to recommend that everybody does here, is just drag this down to the bottom. And then now, you can scroll this down. You don't really need the list of processes. What's important is that you get, let me start this over. What's important here is that you get your memory utilization showing up, and then you get these 4 bars, which each represents 1 CPU core. So the machine that we launched has 32 gigs of RAM and 4 cores. And so you're going to see this start to fill up as we run some things. Okay, so the idea is like, and the way that, again, I'm going to run through this is that I'm going to give you all time now to kind of run through this notebook yourself. And I'm going to set a timer just so that way, we're kind of keeping up with the session. A lot of the stuff in the notebook, you're going to be able to kind of run yourself. You can just kind of go through each cell. And then I'm going to park this notebook a little bit farther down to a different section. So go ahead and run through these. A lot of the stuff, again, this code should be very familiar to you already. And then it'll all kind of run. This should only take, the actual runtime of all these cells in total will take less than 2 or 3 minutes. But then I want you to get all the way down to here. So you'll see the results that it's not going to be a great model, but I want you to get down to this section where it says like, hooray, and then we'll all kind of check in there. But I want you to run this O2 single node notebook, go through it, watch the resource utilization as you run things, and then come back here. And I'm going to set a timer for, let's do 5 minutes, and then we'll see how everybody goes. So I'm not doing this to rush you. I'm doing this just to kind of like keep the session moving. So don't see this as like a thing there. You have to finish it, but the idea is you can run through the notebook and then we'll check back in soon. All right, cool. So the idea there is that we were going through just like a regular Scikit-learn pipeline, and I'm going to run through it now. I had my notebook run as well, so hopefully everybody's kind of been able to run through that. So I'm going to kind of just breeze through the code and just like talk about what's going on. So what we're doing here is we're just loading up a CSV file with pandas. The data is fairly clean already, so we can see this kind of New York City taxi data. One row in this data frame represents a taxi ride that was taken. And then what we're going to do for the machine learning exercise is predict like the tip fraction. So basically like this tip amount right here, divide that by the total amount. So see if we can predict based on the ride if it's going to be a good tipping ride or not. So this is where my notebook messed up because I didn't actually fill it in. So in this case, our data frame here has 7 million rows. So that's a pretty good sized data frame to operate with, like in Pandas. We can see it kind of sitting in memory. I'm occupying like 3 gigs of RAM. And this is like a gig and a half of memory, like sitting in RAM, this data frame. So we can just do like our regular pandas and NumPy stuff. This is just, doing some explaining. And so looking at the like machine learning part, we have to take this raw data frame and create some features for the machine learning. So at this point, we're still doing a lot of Pandas stuff. So these are just column names that we're going to be using later on. These are our features. And then this is the column that we're predicting. We're going to do a regression of this tip fraction. And so that's what kind of is happening here. We're mostly extracting like time-based features out of the pickup time. There's a lot more that you can do with this data set. The focus of this workshop is not really like to make the best ever machine learning model, but the idea is to like kind of scale out our work. And so now this is what our data frame looks like for predictions. We do our train test splits like usual. And so now I have a training data set and test data set. So this is just a typical scikit-learn pipeline. Since we're doing a linear model here for regression, and later on for the grid search, I want to tweak some of the parameters of the grid search. So it's like an L1, L2 ratio. So that's why I'm using the elastic net here. And so we can kind of tweak this L1 ratio to get different regularization in the linear regression. So to see we train a single model, that's not bad. It only takes 7 seconds to train. As I'm running this cell, you can see the memory kind of increase, and you can see the CPU start to process. But just it takes a few seconds, and it's a really bad model because like if we're predicting the tip fraction, those are things that are anywhere from 5% to 20%. For the RMSE to be 5, a whole number, is really bad. But again, we're not trying to make the model better. We're just trying to have it train and run faster. So that's kind of where we're at. And again, that should be mostly a review for things that you're already familiar with. And then we're going to dive into things where it's like, okay, that was loading a data set, training one single model. But when you're actually in this kind of machine learning world, you're going to do a lot more things than this. You're probably going to be tuning a bunch of hyperparameters. You're probably going to be using larger data. You might need to kind of do some other types of processing, predict over a large data set and then train with large data sets. So these are the scenarios where it's actually like going to fail. And I have a different notebook here that already is finished executing. You can totally run through some of these cells. Just a warning, some of these might actually blow up because that's kind of the whole point of this, is some of the stuff here that we're going to try to do isn't possible. So I'm going to pull up a notebook that I already have finished. Again, you can run through those cells yourself, but I'm really going to talk through these components, and then the really hands-on parts are going to be with Dask. So the first step is tuning hyperparameters. So this is something where we can use the same data set that's in memory. We're training that elastic net model, but we're just training a bunch of them because we need to figure out what's the best parameters for this L1 ratio and then for alpha. So this is just like a sample grid. This isn't the real thing. You might be doing different parameters, but I'm taking that pipeline that we already defined above, which is the scalar and then the elastic net. And then now we can then run a grid search right here. So I actually took a sample of this because if you were to try to run the grid search with the full data, it's just going to take a long time. It'll finish. It's just, again, it's going to take a long time. And really, just for the purposes of this exercise, we're going to tune some knobs just to kind of get the points across. But if you look at this here, this grid search now took 30 seconds on the single machine with 44 different model parameter combinations. So it works, but if you were to expand that grid, if you were to use the full data size, and you can go ahead and play with this yourself, you might end up just kind of waiting a long time. It's something that's going to work. It's just going to take a while. So we can do better. We can scale out to a cluster, and we'll see that soon. The next thing is, and this is the part that's actually going to blow up your Jupyter server or your kernel if you actually try to run it, is then we just want to load a bigger data set. So this data set, we loaded just one single CSV file from the taxi data, which just covers 1 month of data. In this case, we want to try to see if we can train a model with the data from all of 2019. And so this is just doing S3FS stuff just for us to get an idea of the size of the data. So here we can say, so for 2019, we have 12 files. They're around 500 megabytes each. In total, they're around 8 gigs. So that sounds reasonable. Okay, I have 30 gigs of RAM on this machine. 8 gigs sounds reasonable. But what ends up happening is it's not going to really work. So spoiler. But the way that you would do this is, you would define some kind of function that loads a CSV with pandas. And then I would just write a for loop, right? So I'm going to say load one CSV, keep it, load the next one, load the next one, load the next one. And that part will probably work. Those 12 individual data frames will be able to be held in memory inside of your Jupyter server. But then right here at the bottom, when I want to concatenate them into one data frame in Pandas, Pandas has to make a copy of stuff, and then it's going to blow up. So you're going to kind of get to this situation. So this is where it'll kind of fail. This kernel will die, which is totally fine. The machine will still be up. And so that's one of the first scenarios that we're going to walk through, is that we just plain old can't load all this data into a data frame with Pandas on a single node. Another thing we're going to look at is, okay, so let's say we kind of put that part aside, and we were able to train a model with a small sample. But let's say we train the model with a sample, but then now we need to make some predictions for some other large data set. So this is like a specific machine learning use case. You might not always need this, but this is like that batch inference type thing. So you have a model that's trained, and then you can't load the full data frame into memory. So I can't just load the data frame and then run predict with that. But you could load each chunk into memory individually, run predict on just that chunk, keep your vector, your array, and keep a collection of all that stuff, and then concatenate them at the end. So this part will work because you're only loading one data frame at a time in memory, but it's going to be pretty slow. And see, this took 8 minutes just to do that, mostly because of downloading files. And you have to write this for loop, and you kind of have to like think about a lot of stuff that it gets really complicated really fast. And so that's one scenario. And then the final scenario is we couldn't load the data, the full data set, right? So we can't even train a model with the full data set. So let's say, if I had 10 years of tax data and I wanted to use just 2019 as my training data set, that wouldn't even fit into memory of this machine. So we're just plain old stuck. You can't even train the model. You have to do some sampling or something like that. And so that's where, drum roll, Dask comes in. We're going to use Dask to, first of all, do the things that weren't possible, which is just loading the giant data frame, training the model with the full data set. But then also we're going to cover the hyperparameter case and like the batch inference case, where they technically do work on a single node, but it's either kind of clunky or it's really slow. And so Dask is going to kind of solve all of these problems. Cool. Okay, well, so before we do that, I know we've kind of just did a lot of stuff of like going through Saturn, introducing Dask. I introduced this kind of single node workflow. And I think this is a good point for a break, because I don't really want to just like keep everybody on the screen attached. I know we're kind of all home doing things, might need to take a quick break. So let's take a quick like 10-minute break. I'm going to set the timer here on my screen so you can kind of walk away, just check on the timer to see when we come back. But if you're on Eastern time, it's going to be around 1:58. We're going to come back, and then this is kind of my like cliffhanger for you, is that they'll come back, and then we'll do all of our scaling Dask stuff. That's going to be really fun. So, and if you have had any issues, this might be a great time to kind of post in the Slack. Stephanie's on there. I can kind of take a peek as well if you have any issues. So I'm going to set a timer for 10 minutes, and then we'll come back and get going again. All right, so just to recap what we went through in the first section, just kind of an introduction into Saturn Cloud, like how to use that, what Dask is, and then how we can use Dask, or ideas of how we can use Dask to scale out machine learning, and then kind of dove through this code of this kind of like single node, like typical exercise that we're used to. And this back half of the workshop is really going to be getting like hands-on into Dask scaling stuff. So the first thing I want everybody to do before we move on to the next notebook is make sure you actually shut down your kernels if you have a couple other notebooks running. So especially if you dove into the advanced section of the second notebook, your memory might be kind of eating away quite a lot. So I want to make sure that we don't have any issues there. So either from within the notebook, you can click this kernel button and shut down kernel, or even you can just do shut down all kernels. You can do that, or you could even do it from here, this kind of kernel session pane. I'm going to go ahead and shut down my other ones that I've got. Okay, so what we're going to focus on here now, I'm going to close this one because I have the done one. I'm going to close that. Now we're going to move over to this hyperparameter notebook. So there's two other notebooks that are kind of doing Dask things. Is this hyperparameter notebook and then this large data set notebook. So kind of exactly what this sounds like. We're going to focus just on the hyperparameter example for this notebook, but along the way, it's going to introduce Dask and other things. My hyperlink didn't work. Oh, okay. Anyway, so click on that 03 hyperparameter notebook, and we're going to jump in there. I'm going to bring this htop window down. You can still keep it up on your screen if you want. So here we're going to go through that scenario where it did work on the other notebook. So let's look at this hyperparameter section that we had here. For this thing that we did with the 10% sample, it took 30 seconds. So kind of keep that in your brain, and we'll see how things work from here. So what we'll do together is I'm going to kind of run through a few of these cells, because this is really critical for using Dask and then using Dask with Saturn Cloud. So we have this Dask Saturn package here. And so this is the way that you can basically interface with your Dask cluster inside Saturn Cloud from your Jupyter server inside Saturn Cloud. Those other deployment mechanisms that I talked about with Dask, like the Kubernetes or Yarn or other things, they all have kind of their own cluster classes that you would use and kind of have to set up behind the scenes. But as long as you're running inside of a Saturn Cloud notebook or you're attached to this Jupyter server, you can use the Saturn Cloud package and then it kind of just like automatically comes together. So we're going to import a Saturn cluster, which is that class of how you actually get a Dask cluster. And then this line here is initializing a distributed client. So this is pure OSS Dask. And so this is a way for you to kind of interact with your Dask cluster. So this client is like your entry point into your cluster. So you always kind of need to have a client live if you're going to do any Dask things. And then if you want to do Dask things with a cluster, you want to make sure that your cluster is live and then also attached to your client. So we could run this cell. It should run immediately because our cluster is already up. So you notice here that there's these arguments that you can specify. So I showed you that UI from within the Saturn Cloud UI where you can kind of edit your Dask cluster from Saturn Cloud. That's if your kind of server is off or whatever and you're not in the Jupyter. So that way you can kind of like pre-specify your cluster and then spit it up there from the UI. If you were inside of a Jupyter server and let's say you were coding stuff and you didn't think you needed a Dask cluster, but now you do, you can also just go ahead and initialize it straight here from the code. And these arguments are the same arguments that you saw on the screen from the UI. This is really helpful, especially when you're like sharing notebooks with people for reproducibility purposes. So I always like to put in, like once I have things settled and once I know what I'm doing, I like to put in the exact kind of hardware specifications, number of workers, number of threads, and things like that. Number of threads typically is equal to the number of cores that your worker has. So in this case, my worker has 4 CPU cores, so we set n threads to that. There's some more information on the Dask docs for details on that, but generally, that's the general best practice. So within Saturn, if you want to see like, because these strings, you might not know like how many cores and how much RAM is in this medium size. We have this function here that you can do this describe sizes function, and it'll tell you like gives back a dictionary of all the different sizes. So this will match up to what you see on the UI, but then this is the key that you're going to use when you're kind of specifying it from the code. So in this case, we're using an X large for the worker, which has 4 cores and 32 gigs of RAM, but you can use any sort of these machines. And I saw on the Slack channel, there were some discussions about the pricing. So if you're curious about the pricing, you can go over there and Hugo even put a little formula for you to figure out like what the different pricing is based on what you're doing. Okay, so a little bit more about the client. So up here, so this is like that kind of code that you're always going to have inside of every notebook that you're running a Dask cluster or you're running Dask with, right? You want to initialize a Saturn cluster and then you need to initialize this client. But like, what is this client? What does this thing actually do? So I'll show you that. So if you just kind of preview this client object, it spits out this little widget here that tells you things about the client, and then it tells you things about the cluster. So this we already know. We know there's three workers on the cluster, the cores, and the memory. Here, what's important from this piece is this dashboard link, because you're going to want to keep track of this Dask dashboard as you do Dask things. So the same way that we did this HTOP down here to kind of like watch what utilization was happening on the Jupyter server, this dashboard is going to give you a lot of information about what's happening with your Dask cluster. So this homepage here, you'll see this light up as we do things, and I'm going to kind of rearrange my windows in just a second. But if you wanted to just check like resource utilization, you can click this workers tab, and then it'll tell you there. So now we can see my 3 workers that are here. Let me zoom in a bit for everybody. We can see our 3 workers here. I can see they're not really doing much. They're not really doing much memory-wise either, because I haven't really told my cluster to do things. And then you can kind of click through kind of some of these other tabs. The system tab will tell you information about the scheduler specifically. So I can see the CPU memory of the scheduler. And then if I wanted to check back on the workers, I can do that here. But for purposes of like this, as we're doing stuff, most of the time you're going to be focusing on this status page right here. Okay. And so what I want you to do is open up this Dask dashboard somewhere. You're probably going to have a little bit more real estate than me. I'm kind of keeping this limited here for just to kind of show you all the windows in the workshop. But what I typically like to do is kind of grab this window, like I'll put it somewhere else and kind of rearrange things to watch the dashboard. And it's responsive, so it'll kind of resize as needed. But I'm going to do that and close this just so I can show you things as we're going. Okay, this has some old tasks that I ran before, so that's why. Okay, so there you go. So that's what you're going to want to watch. You want to make sure that you have your Drupal lab here, you have your Dask dashboard, and now you want to have your Zoom window open so you can see me. So hopefully you're able to kind of rearrange and bounce between all these screens. Oops. And so the one other function I want to introduce here is this wait for workers. This is going to execute immediately for you right now because your cluster is already up. But a Dask cluster, you can actually like resize it and add more nodes and take away nodes. So this wait for workers button will be like if you decided to actually scale your cluster. And I thought I put something in here, but if you wanted to, you could do something like cluster.scale. And then that will change this number of workers. Don't do that right now because we want to make sure that we're all following along and all of our stuff is running at the same timings. But if you wanted to later kind of play around and see with like, oh, if I add more nodes, if I add more workers, how much faster is my code? And you'll kind of see that relationship. You can do this scale followed by this wait for workers because it does take a few minutes for each of the workers to come up because it's provisioning EC2 instances and then it's pulling a Docker image. And then you can kind of watch all of that stuff from the Saturn UI. So beyond just what you're working on in the notebook here, it's helpful to kind of go back and forth to the Saturn UI. I can see my Dask cluster is running. This dashboard link is also available right here from Saturn. So in case you lose your place in the notebook, you can always come back to Saturn. And then you can click this status link, which will give you information about all the different hardware. So we can see our scheduler here, our kube cluster, and then our workers. So we can see I have 3 workers running. If you were to run that scale command, you would see more workers pending, or if you're scaling down, you would see them kind of turning off. And then you can kind of jump into here too and see more logs. So this is as you start to do more things and things fail or whatever, you can kind of keep track of what's going on here. Okay, great. So the first exercise that we're going to do is scaling out the hyperparameter search. And this is taking the exact scikit-learn code that was already in our other notebook. You'll see this next cell is one big giant cell where I just copy and pasted everything from the other notebook. And this is kind of that bolt on Dask for only when you need it situation. So it's like if your data fits in memory, your model itself, it'll train just fine on a single node, but you want to do a grid search and then it takes some time, you can utilize this job-lib backend. So basically, scikit-learn, anytime you're using a model that has this njobs parameter inside of scikit-learn, there's this job-lib interface where you can actually, other outside kind of parallel computing tools can hook into that to spread your work across whatever cluster or whatever parallel computing paradigm that they use. So scikit-learn itself will already parallelize to your single machine. So like we looked at this grid search code, I set njobs -1, which means it actually is going to use all 4 cores on this Jupyter server. But when I use the Dask job-lib backend, I can now scale this out to my whole cluster. And so that's what we're going to see here. So run this cell. It's going to take a few seconds and then kind of stop right here where it says success. And I'll give everybody just a couple minutes to run these cells. So don't get quite to this DaskML section, but right here to this job-lib backend. So I'll set a timer there for, maybe just like 3 minutes to get everybody able to run that. Okay, so run your O3 hyperparameter notebook all the way up to this kind of job-lib success thing, and then come back and then I'll talk about it a bit more. All right, so I ran those cells myself too. So hopefully you've kind of gone through that. Like I said, this cell right here, cell 5, is exactly just a condensed version of everything we did in the single node notebook, all the way up to kind of just defining the pipeline and then defining the grid search object. So none of that code changed at all. Really the only difference of what we had to do was, besides, of course, initializing the Dask cluster at the top, is we just had to import job-lib and then use this parallel backend saying to use Dask. Even this grid search fit code is exactly the same. So hopefully you ran this yourself. If you didn't, I'm going to run it again and just kind of show you the dashboard so you can see things moving here. And so now we can see that scikit-learn essentially is using job-lib to dispatch jobs to the Dask cluster. So we can see that there's this kind of batch of fit things kind of going on. And then that happened in 17 seconds. So compare that to what we ran on the single node. which took 30 seconds. So that's not bad. There's a little bit of overhead to send data to all your workers, but that's half the time. So, we had 3 times the amount of hardware, half the time of runtime. So, okay, you still get some improvements. But again, this is just like bolting on Dask to your existing Scikit-learn pipeline. There are kind of better ways to do this, but I want to just describe this one. There's a caveat here that this joblib thing is only really useful for small data scenarios. So it's really if you have a small amount of data and you're doing some grid search or you're doing some random forest, anything that has this n jobs parameter here. But the reason that it doesn't work for large data sets is because this data frame actually has to be sent through the scheduler, through the Dask scheduler to all of the Dask workers. And then they kind of each get one of the individual jobs. But that IO and transferring the data can cause a lot of problems sometimes. So this really only works for small amounts of data. The next thing we're going to look at is actually going to work for data frames like as big as you ever need them to be. So it's jumping ahead. Like in the next notebook, we're really going to take a deep dive into what a Dask data frame is, how it works. So for now, just run this cell. Trust me, we're going to talk about what it's doing later on. But what I want to focus on here is this hyperparameter code and show you how Dask has its own kind of classes, and you can use those. Feels a lot like Scikit-learn, but it runs a whole lot faster. So this is the next section. This one actually has an exercise, so you really have to pay attention and write some code. I think the exercise is pretty straightforward, and I give you a good hint. But next section, let's take a few minutes again on this. Get to Dask ML, run through these, and then stop really right after the exercise and when you get to the end of the notebook. I'm not going to run this because I don't want you to cheat, but run your Dask ML section, look at this code, take a look at it, and then run this exercise. I'm going to give that 3 minutes again. Okay, and we're back. These codes should have actually run pretty quick for you. So I'm gonna, in case you weren't able to do it yourself or you're just kind of watching along, I'm gonna pull up my dashboard here and I'm gonna run these cells. Again, we'll talk about what this Dask data frame thing does, but the key here is that we're now getting a Dask data frame instead of a Pandas data frame. And then we're defining a pipeline and we're using very, very similar. Again, this code is really, this section of the code is kind of exactly the same as what you've seen before, except the difference now is we're using the Dask ML pre-processing class and a Dask ML grid search class instead of the Scikit-learn one. So look, we're using the Scikit-learn pipeline and we're using the Scikit-learn elastic net model, but we're using Dask's grid search class to kind of run the grid search for us instead. So I'm going to kick this off and I'm going to cheat. I'm just going to go to the answer and run that. And then now we see a little bit more going on in the dashboard. And sorry for my screen is too small, but we see a little bit more of like, here's actual elastic net models getting fit. We see the pipeline going. So this is like Dask itself, and I'll kick that off again just so we can see it. This is Dask itself doing all the orchestration, showing you all the functions that it was running. With the previous joblib example, all we saw was just some like task that was dispatched, but this is actually all the individual pieces because Dask is kind of a little more tightly involved in like what's happening here. But we still kind of started off with a Pandas data frame. In this case, we converted it to a Dask data frame and ran that grid search. So this will work just like that if you needed, your data starts off in Pandas, or if you have a larger Dask data frame and then you wanted to do a grid search with it. And again, we're going to talk about what that is. But see, this one is even faster than using the joblib backend. That's because Dask does a lot of optimizations, and that's the reason why Dask has its own grid search class. It doesn't re-implement everything inside of Scikit-learn, partially because Scikit-learn is huge, but partially because Scikit-learn has some kind of good performance with some of the stuff that they have. But in any cases where it's helpful to have re-implemented parallel kind of algorithms, that's where Dask comes in. But it matches the same exact API as Scikit-learn. Like this grid search CV is the same thing. It takes in a pipeline and parameters, and then you fit it the same way. But in this case, it's a lot faster. So again, you can play around with this yourself, like add more parameters here, use a larger data set, train different models, use different things, play around with it, add more nodes and see how that kind of changes. And then you can kind of see how we can really, really accelerate our grid searches with Dask. So any questions on this part before we jump in more? Okay, great. All right, so we're going to jump over to the next one, and this is really our deep dive into Dask. We might not get through the entire notebook in this number 4 notebook, but that's okay. We're going to just kind of introduce some key concepts and run through it, and then we'll kind of see how the time goes. But again, you have this notebooks, you have this project set up. This is going to stick around after this, and you have some free credits even if you want to keep going. So just like we did before, I want to shut off the kernel for notebook 3 just to make sure in case there was like a lot of stuff that you had loaded. And let me clear my H tab from rearranging my windows. Okay, so now I have a clean slate, and now we're going to jump into notebook number 4. Okay, so similar idea. Notebook 3 was addressing specifically the pain point of hyperparameter search. Notebook 4 here is going to address all of the other things that require loading large data sets. The reason I put the 3 in the other notebook was because you can actually start off with data that was just inside of Pandas. You can start off exactly with your Scikit-learn code and kind of like bolt on Dask via joblib, or import a couple Dask classes and then have that scale. In this case now, we're going to be starting from Dask. And for most of this, we're going to intermix Pandas and Scikit-learn here. And you're going to see that there's a lot of options for doing things because of how tightly integrated Dask is with the PyData ecosystem. There's a lot of options. And so you'll see some of those options. And then we can, of course, discuss, depending on your workloads, what might be the best options for a lot of these things. So we'll start off by, and so this is what we're covering specifically, is the loading the large data set. That thing just completely blew up, right, when we tried to do it with Pandas. Predicting over the large data set, which we were able to kind of hack together a clunky solution with a for loop. We'll show how that's easier with Dask. And then training a model with a large data set, which we couldn't even get to at all because we couldn't even load the large data set. So that's what we're going to do. So here I've condensed the cluster initialization code. So this will be ready for you. Again, if you want more details on it and some more of the stuff that we dove into specifically, go to the other notebook. But here, we're going to start with this loading and processing of the large data set. So let me just give me 1 second. Let me review what's in here so I can see where a good stopping point might be. Okay, this is good. So go ahead and just run these cells, read through this, kind of see what's happening. We're not this up to this next exercise. There's not a lot going on from the code perspective, but go ahead and run through all of these cells all the way up until this number of rows kind of exercise, and see if you can run through those cells and see the output of it. I'm going to give this one just like 2 minutes because there's not a whole lot going on here. Okay, great. All right, so I'm going to walk through this. Hopefully you ran those cells. Okay, so the key here is a lot of these imports are the same stuff that we set up before, but you see a few new Dask ones. So we're importing Dask here. We're importing the Dask Dataframe library as DD. So normally you would import Pandas as PD. Dask Dataframe has a very similar API to Pandas, so you'll see that the code looks similar. And then we're going to import this wait function, which I'll describe in a bit. We didn't use that quite yet. So when we're doing the Pandas read CSV, right? So let me jump back over to a Pandas read CSV somewhere. We just kind of read a single file. So in this case, I did s3.open because we're doing like anonymous S3 access, but that just kind of like opens up a file buffer. But this is the file that we're grabbing. With Pandas, you say load a CSV file. That's it. With Dask, because it's operating in this kind of like parallel computation manner, you can actually tell it to load a bunch of CSV files. So in this case, I'm going to use this glob syntax to tell me, give me everything that's from 2019 on like star. So anything in this is giving me 2019, 1, 2, 3, 4, 5, blah, blah, blah. And so now Dask will be able to kind of load those. It doesn't actually load them all immediately. And here's where we're really starting to get into a lot of the Dask concepts. So what Dask actually does when you run this read CSV command, this taxi object isn't really a full data frame that's materialized in memory, right? This isn't even happening on my Jupyter server anymore. This is something where Dask is figuring out where all these CSV files live. It's probably figuring out a couple data types in here and there. And then this object, when I go to preview it, it kind of knows what the column names are, but that's all it's showing you. You know, when you preview a Pandas data frame, you would actually get the first few rows, right? And so this is telling me now that there's 127 partitions. And so that's the key thing to think about when you're working with Dask Dataframes. Is essentially what it does is it's a logical data frame that's physically chunked across your cluster. And so Dask is saying, okay, there's 12 files here. It's deciding that it's going to divide those 12 files into 127 different chunks or partitions. And so when you run any sort of operations with this taxi data frame, it's actually, Dask is actually going to go in parallel, load some chunk into one worker, do what it needs to do, load some chunk into another worker, do what it needs to do, and then it'll collect your results back for you. And so when you compute something like length, which you did here, and you notice that this actually took quite a while to execute. This maybe took like 30 seconds to run, right? But if I compute the length, we see here that there's 84 million rows. So that 84 million rows, there's no way that that's fitting in my Jupyter server. And you can see here that my Jupyter is not using any memory, but now my Dask is. So like if I go over to this, the workers tab, we can see that now, actually not much is being used now because I was actually not running anything. And so that's kind of like the key stuff to think about with Dask, is that it's doing things in like a parallel manner. Any object that you're operating with is more of like a logical thing that's wrapping a bunch of different chunks. And what's a key part of this actually, and I haven't even showed that here yet, but I do want to show this to you, is that this taxi data frame, those individual different partitions are actually real Pandas data frames. So if I were to do something like grabbing the partitions from taxi, say there's this kind of like collection here, and I'm going to explain what compute does in a second, but if I grab this, I can see that this individual partition, there's 127, is actually a Pandas data frame. So if I do a type here, you can see that this is a Pandas data frame. But if I did type from my taxi thing, that's a Dask data frame. So that kind of illustrates the fact that a Dask data frame is a logical collection of a bunch of Pandas data frames. And so when you're doing things with it, you kind of want to think about that. So it's like, you know, if you're writing some custom functions, and we're going to do that later on, think about that you're kind of operating with Pandas. And the Dask data frame API, again, mirrors the Pandas data frame API. It doesn't cover everything exactly, but it looks similar as well. And here's something where, and so I kind of talked about this. And so that's the key concept I want to introduce to you first, is that a Dask data frame is a collection of Pandas data frames. The next concept we need to talk about is go into more of this idea of lazy evaluation. So Dask is written in such a way where you can analyze data sets that are larger than memory. So like if you're using a single machine or using a small cluster, and even your cluster doesn't have enough memory to load the whole CSV file, Dask can actually still do work. This also enables it to parallelize and kind of send out different tasks. But it can be confusing when you're first using it, in that it's unfamiliar because you're used to having your full data set loaded into memory. Anytime you do something with Pandas, it gives you an answer immediately, right? So if I were to do something like shape, this is a good example. Gives me the shape of this Pandas data frame. But if I were to use this Dask data frame and do shape, I get this thing now that's this delayed thing. And I don't know what that means. And so essentially that's part of Dask's kind of lazy evaluation. So you see how this returned immediately, even though that length call took a few seconds. This is because Dask is just keeping track of the work that needs to happen to compute this kind of row count, but it hasn't even actually done it yet. So if I wanted to actually do something is when I call this compute on this delayed object. So if I were to run this, we can see now my dashboard is going to start to do things. Should. No. Okay, something's going on weird here. Oh, there we go. Just took a second to load. So what this is now doing is computing that same length. It's the same, shape 0 is the same kind of operation when you're dealing with a data frame as length to get the row count. And so what this is doing now is Dask is going to S3. It's grabbing those individual CSV files. And maybe I can show you in the graph. Might be a better place to do this. So you can see the graph of tasks. So Dask is actually figuring out these 127 different chunks and these 127 different partitions, grabbing the files down, it's computing the row counts individually on all those different partitions, and then it's going to give you back the answer together. So I don't know why this graph isn't loading, but that's okay. This dashboard is having a hard time. Okay, it's probably because I'm running too many things at once. So that's the key concept is when you're doing things and you get this delayed object back, you will need to run compute to kind of get your answer back. So I'm going to skip this exercise, or I'm just going to give you the answer just for the sake of time. I see we have like 25 minutes left. And so it's the same concept here when we're trying to get like the memory usage. So if you were to run compute, which I think I do right here, if you run compute on that, it'll actually give you now the actually like memory size. So compute is useful when you are trying to get back like single numbers, or you're trying to get back like a small part of your data frame. So if you notice earlier, I ran compute on this partition 0, and it gave me back a pandas data frame. If I ran compute on just taxi, it would blow up because it's actually going to try to give you back the entire distributed Dask data frame into a pandas data frame on your Jupyter server. So that's not going to be a good time. So definitely don't do that. So the question here is then, because Dask does this whole lazy evaluation concept, each time I want to get a row count, it's going back, reloading CSVs, pulling them down from S3, parsing them, computing things in parallel, and then giving it back. What if I wanted to like kind of cache that or execute that graph of tasks ahead of time? And so that's where this persist method comes in. So what persist does is very similar to what compute does. It triggers computations that have been kind of built up for the lazy evaluation, but it keeps the results in memory on the cluster. So essentially now this taxi has an object where I told it to load CSV files, right? So what this persist command is going to do, and I'm going to run it and you're going to see the dashboard update, is that Dask is now going to S3, pulling down all the CSVs, but then it's going to hold everything in that Dask data frame into memory across the cluster. So we see now that these bytes are starting to kind of build up because it's holding it now into memory, still spread across the workers. So each of the workers are going to get some certain amount of chunks of this data frame, and then it's going to be persisted here. But now what's going to happen is we're going to see that the operations that we do later on are going to execute much faster. And so also one thing that you notice is that persist call returned immediately, because Dask ends up doing this persisting work behind the scenes, so that way your kind of client can keep running. If we wanted to actually wait for it to finish, oops, messed that up. That's where this wait function comes in. Oh, it actually just happened to finish at the same time. But if you were to run the persist and then run wait, I do that a lot. I usually run persist and wait because I always want to make sure that my stuff gets triggered ahead of time. So now when I want to do something like length, let me just show you length first. It's going to execute super fast, just like that, because all the data is already now sitting in memory across my cluster. Dask didn't have to go back to the CSV files. So now we can compute the size because I didn't want to wait for the other one. And so remember our other data frame in Pandas was like 1.5 gigs. In this case, now we're dealing with a data frame in memory that across the cluster is 16 gigs total. But we're going to need all the rest of this RAM for the other stuff that we're doing. Any questions on loading Dask data frames and kind of the lazy evaluation or persist or compute or anything? Okay, great. So we have an advanced topic here. I'm going to leave this for homework where you can go through and kind of dive into this. This is this Dask delayed functionality. Basically, think about this Dask delayed as the building blocks of all these other higher level APIs. This is this individual task kind of execution like library. So go through that. It's really powerful. I find that I use this Dask delayed a lot. For basically any time something doesn't fit neatly into like a data frame paradigm or an array paradigm, Dask has parallel arrays as well. Dask delayed is really, really helpful. So we're going to skip that for now. Okay, so exploratory analysis. This code is going to look a lot like the Pandas code. This is calling describe, and then I can just kind of round it. But notice this call to compute here, which is different than what you would have seen with Pandas. And so now Dask is doing all this stuff in parallel across my cluster. Okay, so this feature engineering code, and we're gonna, okay, and here's the stuff. So now we can see like stats about our full data set. Let me just peek ahead, make sure and see where we're going. Okay, so just follow along with me here. We're gonna get to some exercises very soon, but This feature engineering code is really cool because it's actually exactly the same as was in our Pandas notebook. So of course, this part's the same because the features are whatever. But this prep df function is exactly the same. Like if you don't trust me, you can go ahead and copy and paste it from the notebook number 2. It's exactly the same because it's one of those things where the Dask Dataframe API mirrors the Pandas Dataframe API. So it's really nice because you can actually even utilize that same function. So now when I run this, this looks just like Pandas. I can now preview my data. The difference here, though, is that all this stuff doesn't really execute across the entire data frame yet because of this whole lazy evaluation thing. It only executed on the first 4 rows because I asked it to give me a preview. Okay, so we have 2 more concepts, and there's only 20 minutes, so I might not get through all of it. But the final concept was like training on a large data set, which is actually kind of, from a code perspective, a little anticlimactic because it just looks like Scikit-learn. So there's not a lot of extra concepts you need to learn. And that's the great part, is that you can kind of use things that you're familiar with. So I'm going to jump down actually to that section. The next thing I had here was predicting over a large data set. But I at least want to show you the training section. I don't want you to run it now because we're going to come back. I want to introduce a couple other concepts to you. But I'm going to scroll down here to the training model with a large data set. So the main takeaway here is that the Dask ML library looks and feels and operates a lot like Scikit-learn, except now you're dealing with Dask Dataframes, Dask arrays, and then Dask ML models instead of Pandas Dataframes, NumPy arrays, and Scikit-learn. So I'm going to cheat here again, but you can look at this later. This train test split, again, is exactly the same as a train test split that you would do with Scikit-learn. It finishes immediately, again, because of this lazy evaluation. So what I'm going to do here is call another persist method. So this Dask.persist will actually persist over a bunch of different objects at the same time. I could do them individually and say like xtrain equals xtrain.persist like this. But the reason we do Dask.persist with a bunch of arguments is because these 4 objects actually share a lot of the task graphs ahead of time, because they all start from the same group of CSV files. They all start from the same data frame. It's just doing some data splitting and then picking out columns and stuff like that. So they share a lot of the operations. So I'm going to go ahead and run this, and I'm going to run it with wait. So now we're actually going to persist this, which means the data splitting, now we're executing on the cluster, and then we're holding these data frames and arrays in memory. So you saw my memory kind of increase, but then now I can run some operations on these guys, and it runs really fast. So we see our training data set has now almost 60 million rows, and then our test data set has like 25 million rows. And then the next part is using Dask ML models, right? So instead of Scikit-learn now, you notice we're still using a Scikit-learn pipeline, but now I'm importing the Dask ML linear regression class. So that's a little bit different than the elastic net that you saw from Scikit-learn. But if you just kind of like look up Dask ML and go to the docs, you can see all of the different things. Let me just do that now. So you can go to the Dask ML docs and you can see all of the different kind of things that are here. So, hyperparameter search we covered. There's a whole suite of linear models that have been kind of rewritten to have parallel implementations. And so that's the key, is Scikit-learn has a ton of algorithms, right? Some of those algorithms support parallelism already, so like random forest or grid search, and you kind of use joblit to take advantage of parallelism there. Some models, though, are purely single core. So like a linear model. Whenever I'm running a linear model in Scikit-learn, I see my memory kind of have this big chunk taken, and then I see one core just on 100%, where all my other cores are just sitting there doing nothing. So Scikit-learn has no concept of parallelizing that. So Dask ML actually re-implements some of these models to actually train in a parallel manner, and we'll see that. So in this case, it's linear regression, and you can read through the docs and read through the details of the different parameters and the implementation details to see how it's how things are a little different. But in this case, if I do linear regression with an L2 penalty, that's the same thing as elastic net with an L1 ratio of 0. And then I need to grab Dask arrays. I don't have time to fully explain what this means, but essentially our linear regression kind of class expects a Dask array instead of a Dask data frame, but this function will convert those things for you. And then again, I'm going to just cheat for the sake of time and show you would just fit it in the same way. So you can run this if you want to. It's going to take a few minutes because this is a really big data set. This is a data set with 80 million rows. And your cluster is fairly small. It's only 3-node cluster. So if you did a bigger cluster and you wanted to play around with that, you can actually try it, scale up your cluster, fit the model and kind of see how the runtimes change. This here is going to take you maybe 5 or 10 minutes for this model to fit. But as you do that, you can kind of see the Dask dashboard start to light up and see what's happening. But again, the main takeaway here is that the Dask ML kind of library looks a lot like Scikit-learn. And so I can do a predict, and then I can compute my mean squared error the same way that I would before. And then the same thing with XGBoost. There's a Dask XGBoost package where this all fits on one screen. This is the same way that you would work with XGBoost if you were familiar with that. Okay, so like I said, I wanted to introduce to you mostly just the high-level Dask concepts, how to use Saturn, how to think through some of these scenarios. But you can definitely take a look at these notebooks more later on. There's one last thing that I think we have 15 minutes, we have enough time to cover. And I want to cover this kind of predicting over a large data set, not only just because of this specific use case of where you have a big data set, you need to do like some batch inference. The concept that we're introducing here with this map partitions method is something that you're going to end up using a lot with Dask Dataframes. And so that's kind of why I want to introduce this, because I find myself using this a lot. So I'm going to give you like 5 minutes to run through this section. So scroll back up in the notebook number 4, go to this predict over large data set. There is a good number of cells here, but read through this to get an idea of what's going on. You can kind of pound through these. These cells will run really quick. And then get down to this exercise right here, and then try to work on it. And if not, you can wait or kind of watch later. But kind of take a crack at that until you get down to this exercise here. And I'm going to set the timer for 5 minutes here so you can get going. Okay, and we're back. So I think that was a bit of a little meatier part of just like a lot of different cells and concepts to think through, but I'm going to take a quick breeze over that. And then you can kind of go through this notebook again and play around with things, and then we'll wrap up after that. Okay, so the main concept that we're introducing here is not really batch inference. Like, we're using a concept in Dask for batch inference, but this is a much more general thing that can be used in a lot of different ways. This is the map partitions method. So that's a link to the Dask API page. But what this function does is essentially applies the function that you pass it to each chunk or each partition of the Dask data frame, which remember is a Pandas data frame. So essentially it's you write a function written for a Pandas data frame, and then you will tell Dask to execute that in parallel. So this is useful for operations where you kind of are operating in a row level manner, right? If different rows needed to know about each other, you couldn't do it in this method because each function just kind of gets executed like on its own, the whole concept of mapping. But what's nice is that you can use code, any kind of code that works with the Pandas data frame, it'll work with this map partitions method. But there's a couple considerations. So we just grab a partition. I think I already did this earlier actually, but now we have an object that's a confirmed Pandas data frame. So I'm just going to make this dumb little function, which is going to take some column, multiply it by 5 and give it back. So when I run that function on my data frame, this taxi thing here is a data frame, I get back the output, which is now a series, right? Because it's just returning this, right? So that's a Pandas series. And then when we look at the object, you can kind of just preview it there, right? And so that's now, basically what's nice about this is you can then like write some functions, test them on like an individual Pandas data frame, and then that it's going to kind of work across your Dask data frame across all these different partitions. So then you just do that. You say map partitions now with this function. And so again, Dask doesn't actually do anything. Let me bring my dashboard back up here. Dask doesn't actually do anything because it's just building up this graph of lazy tasks. So when I call this head function, it will do it for the first 4 rows, which it can do that because it's just some function that's operating on a block, on a chunk of data. And then it'll kind of give you that back out. So now if I do a type on this guy, it'll be a Pandas series because that was head, right? Sorry, I did type on the wrong thing. Let me do type on the out object. Well, you can kind of already see that it's a Dask series, right? So if I do type here, that's a Dask series object. Okay, back to that. And so that'll work just fine. So now this function will just run across all of my entire Dask data frame. There are some things when you start to do more complex functions where Dask needs to kind of figure out the types. Dask will sometimes, it'll print out an error message for you or some warning and say, hey, I inferred this data type. Let me know if it's right, or be more explicit by passing in this meta argument. So in this case, this meta argument is just telling it, you give it an empty series or an empty data frame, because your function could actually return back a whole data frame. And then you just tell it what the data type is. So that way Dask can kind of optimize and know what to do behind the scenes. So in this case, we don't really need to do it because our function is just returning back a series that's float 64. It figured that out on its own, but it's always kind of best practice to specify types up front if you can. And so in this case, I'm already loading so that's, okay, sorry, before I jump to that. This is the whole concept of map partitions. It's executing any arbitrary function across my partitions, which are Pandas Dataframes. So how I want to use this now for batch inference is I'm going to take some scikit-learn model that I saved out to a pickle file, and then I can just write a function to call predict with that model across all my different partitions in the Dask Dataframe. And so now I get back, so now basically that's where we're at here. So this exercise kind of takes you through doing that. And this is probably one of the more involved exercises in this workshop. But again, I'm going to jump ahead and cheat. But we saved this model file out in notebook number 2. So if you didn't run notebook number 2, this cell will probably fail for you. But we just wrote out some pickle file of a model that we trained in scikit-learn with a small amount of data. We didn't train that with Dask. But now let me just go ahead and jump to the answers and show you what's happening. So now I can kind of define this function that takes that model object, and then it runs predict with whatever data frame you happen to pass to it. And then it gives back a series of the predictions. So now I can run predict with my Pandas data frame, and then that'll run and give me back some stuff, right? So again, this is how I'm testing the function on my Pandas data frame first to make sure that it's working, and then I know that I can run this on the full Dask data frame. And that's the next cell. So in this case now, this is the function that I had where I could just call predict. But now, because I'm working with this Dask data frame, I can call map partitions, passing the predict function, and it'll now run across the entire Dask data frame. Again, lazy evaluation, so it doesn't do anything. But then when I go to compute, so if I compute the length of the scikit-learn predictions, that's pretty small. But if I go to compute the length of the Dask ones, it's not even just computing the length of something, it's running all the predictions with the 80 million rows. So it's taking this 80 million rows, passing it all through that model. Oh, I ran the wrong cell. Passing it all through that model, getting the predictions, and then it's computing the length of the data frame because that's what I asked for. But that's kind of just an example of how you can do batch inference, but in more so, it's an example of how you can kind of execute arbitrary functions against a Dask data frame. So there's another concept here of this parallel post-fit wrapper that we don't have time to discuss now. So the last thing I'm going to leave with, and again, if you have more questions on this, I know we're running out of time, you can ask some questions in the Slack channel. We can follow up. Again, you have access to these notebooks. You have access to this interface for however long you want after this. And so this is just like a review of what we covered, right? So we covered how to use Dask data frames to load data across a cluster. We did some distributed model training. I showed you how to do that. You can run the cells yourself. We scaled a hyperparameter search, and we did batch inference. But even more important than like the actual things that we ended up doing are these Dask concepts that we introduced and covered. So it was initializing a cluster, understanding Dask's lazy evaluation, understanding a Dask data frame, running map partitions, playing around with the job-lib backend, all that kind of stuff. So that's kind of really important concepts that we covered, and you can kind of go back and review those things. Something you might want to think about is, could have I just used a large Jupyter server instead of a Dask cluster? And so yes, Dask works on a single node just fine, and I have some instructions for how you can do that, even if you wanted to do it within Saturn Cloud. The limitation here is that with Saturn and AWS, really, you can get a machine that has like 60 cores and 500 gigs of RAM. And if all your data and everything fits inside of that, you're perfectly fine. You can go ahead and do that. But a cluster is helpful when you need to scale a lot more, and especially when it comes to cores. Because like if I'm doing a big hyperparameter search, I just want like a lot of cores for it to finish really quickly. You're paying the same amount of money, except now you're not having to sit around and wait, right? So I can scale on a cluster and get a lot more cores and a lot more machines than before. But either way, it's going to work out the same for you if your data fits on the single node. So what's coming up next is we're working on some workshops around Rapids and GPU, really around GPU stuff. So like deep learning, Rapids is a project that actually accelerates data science workloads on GPUs, and then doing deep learning things with TensorFlow and PyTorch. Yep, so that's pretty much it. One thing I want to let you know is that, if you're done kind of with the workshop, you can go back over to Saturn Cloud, go to your project page, and then click stop here. The machine will turn off automatically. I've set mine to 1 hour. I think some of yours, if we set it for you, it's set off to a 6-hour kind of auto shut off. But if you have the Jupyter Lab window open, the machine is going to kind of keep running. So if you want to shut that off, when you close your laptop or turn off your computer, that auto shut off timer is going to kick off and then it'll turn off. Or if you want to kind of save your credits, you can go ahead and shut down these servers right now. But with that, I think we're just out of time. But if anybody has any questions and you want to stay on for a couple of minutes, totally happy to chat. But thank you all for joining. Thank you for Stephanie for helping a lot with on the Slack channel and helping everybody out, and the rest of the Saturn team for kind of putting this workshop together. And so I hope you all find some value with it, and let us know what you end up doing with Saturn.